Hello students, so we'll go for the next video of the carbonyl complex. Okay, so in the last video we studied regarding the mononuclear carbonyl complexes and its higher studies. So today we'll go for the next. The most of the carbonyl complexes they exhibit a strong and sharp uh, frequency, okay, vibration frequency band at 2100 to 1800 per centimeter. This is very much important, okay. And you know that the frequency vibrational frequency carbonyl is generally free from coupling with other modes and is in the presence of other vibrations, okay. Alone provide the information, this is provide the valuable information about the structures and bondings of the carbonyl complexes, okay. In majority of the compounds, the frequency of carbon monoxide, okay, of free carbon monoxide is 2155 per centimeter, okay. 2155, 2155 per centimeter, and it is shifted to the lower frequency. So this is what, okay. And in terms of the simple molecular orbital theory, in simple molecular orbital theory, this was observed the decrease the shifting to lower frequency can be explained as that the sigma bond, okay. The sigma bond which is formed by donating 5 sigma orbitals, by donating 5 sigma electrons of carbon monoxide, okay, to the empty orbital of the metal. So I have shown in the last video, which tends to raise the frequency of carbon monoxides, okay, since the 5 sigma orbital is slightly anti-bonding, and the pi, and the second point, we can say that the pi bond is formed by back donation the d pi electrons of the metal to the empty anti-bonding orbital of 2 pi star orbital of the carbon monoxide, okay. This tends to lower the frequency of carbon monoxide. This is what very much important here, okay. This is yes This is what, and although these two components of the bonding are synergic, we say it's a synergic effect. The net result is the drift of electrons from the metal to carbon monoxide, and when the metal is in the relatively low oxidation state, that is what, and the frequency of carbon monoxide of the metal carbonyl complex are generally lower than that of the value of free carbon monoxide. So this is what, and the opposite trend we can observe. But however, when carbon monoxide is complex with the metal halides, in which the metal are in relatively high oxidation state, okay, if carbon monoxide forms a bridge between two metal, like the vibration of frequency of carbon monoxide will rise from 1009 range from 1900 to 1800 per centimeter. So when the bridge between the two metals, this carbonyl, is much lower than that of the terminal. So if you see that bridge will have in this way, but that will be much lower than the terminal, okay. So terminal carbon monoxide, that will be in 2100 to 2000 per centimeter, 2100 to 2000 per centimeter. So this is the extremely low frequency of carbon monoxide is also observed, that is 1300 per centimeter. Very low frequency is observed when the bridging of carbon monoxide groups forms an adduct, okay, via its oxygen atom. So this is what about the fascinating role of carbon monoxides, okay. And by taking this all carbon monoxide, so mononuclear carbonyl complexes and its role, vibrational, this we have learnt in the previous video. So today, if we show for the polynuclear, so polynuclear carbonyls, these polycarbonyls are having a variety of structures. Elucidation of their structures by vibrational spectroscopy is very interesting, we can say. So very complicated and very interesting, okay. Here the principles much principles is involved here. Then the structures of the some polynuclear complexes, yes, as I said, it's very complicated, okay. And elucidation is not only based on the IR, but also the X-ray analysis also have the definitive accurate structural information. So however, the vibrational frequency also helps in the solution of knowing the metal polynuclear carbonyl complexes, okay. Now in general, if you see the terminal new carbon monoxide, okay, terminal is higher than the bridging. So they are the higher than the bridging carbonyl frequency here, okay. Thus if you see in palladium, so PD, palladium twice, if you see this complex, mu CO twice plus 2. Okay, palladium twice, mu means what? This is bridged. Okay, CO twice plus 2 complexes, so which contain two bridging with no terminal. So this is having two carbon monoxide, but there is no terminal carbon monoxide here, that is D2H structure. So this comes under D2H structure. Okay, so this is what if I go for, so this is rhodium, this is rhodium. Okay, so and if you see here, this is carbon, so this is carbonyl like this. Okay, and this is what here, so like this, and this is like this carbonyl. Okay, like this. So if you see the structure, so carbon monoxide, and here it is rhodium, 2 rhodium like this. Okay, see this 1 2 3 4, 1 2 3 4 like this. Okay, so this structure if you see here, which contains two bridging. Okay, so this having the two bridging and no terminal here, so D2H so exhibits two bridging frequency 2027, so it exhibits two frequency at 2027 per centimeter. Okay, to of Raman. So if you see, this is shown by the Raman 2022, but 1977 this is shown by the IR frequency, this. Okay, so this show the two bands, one at Raman, that is 2022, and 1977 IR bands is shown by this this complex, Okay, whereas if you take the another structure, that is platinum I2, okay, CO6 plus 2. Okay, platinum I2 CO6, platinum I2 iodine 2 CO6 times plus 2. If you take this structure here, so that is platinum iodine 2 CO6. So if you take platinum here, okay, platinum, then 1 carbonyl, 2 3 carbonyl. Okay, 4 5 and I2. Okay, so this like this. Okay, if you take this structure, uh, platinum 2 I2 CO6. Okay, if you see this structure, it comes under 2D. Okay, D to D structure, point group. Okay, so if you see this complex ion which has no bridging here, so there is no as such bridging here. Okay, in this here there is no bridging, and D2D, yeah, it is D2D, yes, correct, D2D structure, and exhibits 5 terminal carbon monoxide. Okay, 5 terminal, 1 2 3 and 4 5. Okay, 1 2 3 4 5 terminal. Okay, all are this terminal carbon monoxide, and they exhibits at new frequency of at between 2233 and 2173 per centimeter. Okay, so 2233 and 2173 per centimeter. Okay, so this is how is very much helpful. IR study is very much helpful. And if you see the next complex, that is CO2 CO8. Okay, cobalt 2 dicobalt on octa carbonyl. Okay, which is dicobalt, so I can take it here as cobalt like this. Okay, so 1 2 3 4 5 6, this is 7, and this is 8. Okay, CO2 CO8. So this is what your carbonyl, like this, CO, and this is one carbonyl, and this is one carbonyl. So if you take this complex CO2 CO8 here, okay, so this complex is C2V, so it comes under point group C2V, and the structure has the 5 terminal and 2 bridging frequency, 1 2 3 4 5 terminal and 2 bridging, 5 6 1 7 8, yeah, uh, yes, it's having 5 6 7 8 5 6 terminals and 2 bridging expected, and IR active here, expected to be IR active. Okay, and observed, and the frequency of this was observed at 2075 and okay, and at 2028, so like 1 2 3 4 5 frequency. Okay, of it was observed here. Okay, so this is how you can see that how the IR spectroscopy helps in getting the IR frequencies of the complexes. Even the scientist studied some Schilling, Schilling and Pitzer. Okay, Celine and Pitzer, okay, they studied the measured the IR spectrum of Fe2CO9, okay, Fe2CO9. They studied the IR spectrum of this compound and observed two terminal at 208, and 2034 per centimeter. Two terminal they observed two terminal frequency and one bridging frequency at 1828 per centimeter. This is bridging and these are terminal frequency. Okay, so these scientists they observe for this compound, okay, and one bridging at 1825, okay, 1828 per centimeter of this carbonyl bands. Okay, so this is how and which was very stuck to X-ray diffraction. So similarity between these two we can see. So like this, for different point groups, the vibrational spectra is having the different frequencies. Okay, so this is how the IR spectra helps us in getting the different ranges of as the structure point groups differs here. So we can see that the frequency also is differing. Okay, so even the X-ray diffraction, we have seen that it is very much important parameter of spectroscopy. So where we can see the IR application will have the helping more with the X-ray spectroscopy to know all the correct exact structure of such complicated metal complexes of a polynuclear way. Now, if you see the structures of unusual bridging carbonyl, so some of the structures may be like this metal. Okay, so and they are unusual. These are unusual metal complexes here like this. Okay, so this is one type of bridging here. So may possibility is there, or sometimes you can see like this. Okay, polynuclear. So that's why. So this also is possible here. So like this, like this. Okay, so this is what possibility is there, and sometimes you can see that the metal may have the possibility of binding in this way. Okay, in this way. So like this, these are the different mode of the metal complexes of binding way. Okay, semi-bridging, these semi-bridging carbonyls. So this we say it as a semi-bridging carbonyl sometimes. Okay, and they are present in some complexes like cyclopentadienyl 2, vanadium and pentacarbonyl, such type of complexes. You can see that semi-bridge type of complexes, and their carbonyl bands, if you see, they are assigned at 1871 to 1832 per centimeter. Okay, 1871 to 1832 per centimeter. Okay, and semi-triple bridging carbonyl, if you see this semi-triple bridging carbonyl 3, okay, in this type of complexes. Okay, which is called a semi-triple bridging carbonyl complexes, so found in the complexes like cyclopentadienyl CP, cyclopentadienyl twice, okay, RH3, rhodium CO4, tetracarbonyl, okay, minus. So if you see this triple bridging complexes, and they are showing a band at 1693 per centimeter, 1693 per centimeter. Okay, and is probably due to the carbonyls. So IR band at 1662, and this is what. So this is how the IR spectra helps us to get the semi-triple bridging mode. Okay, so another semi-triple bridging. So here is the third one, semi-triple bridging here. So third carbonyl. So this also is type of semi triple bridging carbonyl stretching vibrations. In some case, you get it in this range as in the sex structures. Third, we have learned like CP, tricyclopentadiene niobium thrice. Okay, CO7. So this is one example for semi triple carbonyl, which exhibits very low frequency of 1330 per centimeter, very low frequency of 1313 per centimeter. So this is how the IR spectra helps us in getting polynuclear. And some, if you see the vibrational spectra reported for polynuclear complexes of unusual structures like Fe6N CO15 3 minus. Okay, Fe6N CO15 3 minus. So which is octahedral point group, and some and you can see that the structures like CH, okay, CH3C CO thrice CO9, CH3C CO thrice CO9. They are having the very unusual type of structures. Okay, so they are also reported. Such type of structures are also reported. So this is how the we can see that the complex. And even the Shriver et al., one more scientist, Shriver et al., Shriver, Shriver et al., okay, who, he also found that the oxygen atom of the bridging CO group can form a bond with the Lewis base, like Lewis acid, like AlE3 triethyl aluminium, okay. And it was shown in CO2 CO8, okay, CO2 CO8. So this is how this one having CO here like this. Then you can see that this is bridged CO2 and CO this way, something in this way. 1 2 3 4 5 6 7 8, like this, something like, okay. So CO2 CO8. So this was shown by Shriver, and observed that this forms an adduct of the following type, like this is going to adduct type of formation. So this was shown by the Shearer here. And as expected from this structure, the adduct exhibits two bridging carbon monoxide uh, vibration here in the IR range, that is 1867 per centimeter, which is 15 per centimeter higher than the other at 1600 per centimeter, okay, which is 232 per centimeter lower than the parent compound. So in cases, this is how the IR spectra is beautifully explains the different structures of the polynuclear complexes, okay. And so this is how we can give it like this: Fe, Fe 1 2 3 4 1 2 3 4, and this is applied with the carbonyl, and this is AlCl3, like this, okay. So this is a suggested structure for what I explained now, just now. So this is how I can say that the IR spectroscopy helps us in most of the cases of the uh, polynuclear carbonyl complexes, okay. And one more, if very interesting, if you want to study, is the carbon complex with the ruthenium C3V, okay. So which is something like that, ruthenium Ru, polynuclear Ru, and you can see that this is bond with carbon monoxide this way, okay, ruthenium. So if you see this complex, okay, such type of complex where iron atom is capping in three metals metal array, okay. So the strong affinity of the Raman as well as the spectra exhibits four polarized bands for this sensitive to carbon 12 and carbon 13 substitution here, okay. And if you see the vibrations of carbon to ruthenium thrice, so it is 1939 per centimeter, okay. And vibration of C double bond C, carbon carbon double bond, you can see it is coming around 1309 per centimeter, okay. And the frequency of carbonyl we can see at 2024 and 1980 per centimeter, 2024 and 1980 per centimeter, okay. These two bands are presumably, you can see that it is due to vibrationally coupled modes between the CCO, that is CCO, and frequency of CO. So this is what of the terminal carbonyl of the terminal carbonyl group directly bonded to the directly bonded with the ruthenium. So this is how and the metal this is more than, I think, more than sufficient to know the vibrational, how it is helpful for the polynuclear carbonyl compounds. Hope you understood this today's subject of IR spectroscopy application on the polynuclear nuclear complexes, okay. So this is what short notes you can make, and some examples you can give, and how the IR spectra they differ whenever the such polynuclear complexes is being studied, and even that will be very boosted with the X-ray method as techniques also. So this is what, okay, hope you understood. Thank you. Have a nice time.